Hey, hi everyone. This is the last topic I want to talk about in chapter 6. It's described in Atkins 6b, the response of equilibrium to changes in pressure and temperature. Here's the basic question. In a previous video, we solved this problem. It was an extent of dissociation of water. So the idea is that we have water which was dissociating into hydrogen and oxygen, H2O gas going to H2 gas plus 1/2 O2 gas. And given some set of conditions, 1 bar and 2000 Kelvin, we can calculate equilibrium constants, delta G's, and all of that. The question is, well, what if we're not at 1 bar? Will the degree of dissociation change if the pressure is 2 bar? Pause for a second. Think about an answer. Welcome back. Here's the answer. And I think that this might be familiar to many of you from Gen Chem. The answer is an unequivocal yes. The equilibrium composition will shift to favor the side of the reaction with fewer moles of gas molecules. Right? That is, it will shift towards the reactants. It will shift towards reactants. There's a general name for this principle. It's called Le Chatelier's principle, and it's the way that we can understand the response of equilibrium to changes in general. Le Chatelier's principle says that when a system is at equilibrium and it's subjected to a disturbance, it responds in a way that tends to minimize the effect of the disturbance. So if I had 3.5 moles of gas molecules as a product and 1 mole of gas molecules as a reactant, it's going to shift towards the side with fewer. You can solve these problems really quick and easy, right? So here's how we make chloroform, methane plus chlorine gas. We want to do this at high pressures. Well, 4 molecules of gas, 3 molecules of gas. If I go to high pressure, it's going to favor the products. And so yes, right, this would be advantageous in this case. Right? Ng equals 3, that's an equals Ng equals 4. Okay, simple enough. Now let me get this a little bit more complicated. If the degree of dissociation changes when pressure is 2 bar, does the equilibrium constant change? Pause and think about this for a second. Welcome back. Let me give you the answer. The answer is an unequivocal no. No, 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 no. Equilibrium constant is not just a clever name. An equilibrium constant is a constant. It does not change. Right? And more generally, the rationale for it is described here. Right? The equilibrium constant is only defined for 1 pressure. It is defined at the standard state. And therefore, it only describes the composition of the system at 1 bar. If the pressure is different than 1 bar, then the composition changes. Let me show you. This was the specific equation that we derived for the dissociation of water. Right? Alpha was the degree of dissociation. Away we go. Look what happens. If P total goes up, right, this expression will increase. I'm trying to argue that K, the equilibrium constant, is constant. Right? So this is a constant. And if that's true, the only way that can work is this quantity decreases. Right? That is, the extent of dissociation decreases. It shifts towards the reactants. Right? The whole reason this works is because the equilibrium constant is a constant. If this changed, we'd be screwed. All right, there's some good problems that I'll put up here on the good old-fashioned worksheet. We can calculate this degree of dissociation at P equals 2 bar. And my advice to you is, be clever when you solve these and solve it without a solver function whenever you can. That's half the game plan. The other game plan here is temperature. Okay? How do systems respond to changes in temperature? And again, the general idea is Le Chatelier's principle. When a system is at equilibrium and subjected to a disturbance, it responds in a way that tends to minimize the effect of the disturbance. Well, as we just write a chemical reaction, how temperature relates to this isn't exactly clear. And the way I think is most helpful to think about this is really to think about whether reactions are exothermic or endothermic. And given that description, I can describe these as either products, an exothermic reaction is producing heat, or as a reactant, an endothermic reaction is requiring heat to go. And if I have that kind of notation, then the idea becomes a little clearer, right? If I have an exothermic reaction, I'm increasing the amount of heat. Sorry, if I have an exothermic reaction and I increase the temperature, right, I'm providing heat to the system, I'm providing energy to the system, and it will shift towards the reactants. Shift this way. Conversely, if it's an endothermic reaction, delta H is positive. When I increase the temperature, I'm supplying energy to the system, and it will shift towards the products. Right? I'm not going to go into a quantitative derivation. It's a little bit longer, and you can see the gory details in Atkins 6b. But the quantitative description of this behavior is called the Van Hoft equation, and I've described it here. So if you're a note-taking person, right, in particular, write this equation down. Natural log K2 divided by K1 equals negative delta H over R times 1 over T2 minus 1 over T1. Right? So a couple of things you can do, and I'll put this up on the worksheet as well. You should convince yourself that predictions from this equation are consistent with Le Chatelier's principle. Right? That is, the sign of delta H will impact whether or not K2 increases or decreases here. The second thing I would point out to you is that this equation may look familiar to you. It might look like something. Pause again. Recognize this one? This was the Clausius-Clapeyron equation. It described the liquid vapor phase boundary in phase diagrams. And if you think about that, right, the equilibrium that this was talking about was a liquid gas equilibrium. Right? The equilibrium expression for that is simply the partial pressure of the gas divided by P standard. Right? The liquids don't appear. And so these are entirely consistent descriptions of equilibrium. All right. Van Hoft equation has two important uses. And again, they sort of mirror that Clausius-Clapeyron equation. Here is the Van Hoft equation. One notion is that if I know what delta H is, I could calculate K at an alternate temperature. So we previously calculated that at 2200 Kelvin, here was KEQ. Let's calculate the equilibrium constant at room temperature, given this delta H. We can do that. Here's the other use. If I know K1 and K2 at different temperatures, I can calculate delta H. And I wanted to give you one example of this. Before I came to Geneseo, I was at the University of Colorado. And this is my old research group. I've mentioned this guy's name to you before, David Nesbitt. He is a world-class scientist. I have the highest opinion of him. Julie was a graduate student working at the University of Colorado, and we had collaborations with a bunch of Germans. That's who these guys are. And what Julie was doing was looking at a biochemistry reaction. Right? So here it is, and I'm going to switch to my laser pointer. This is some RNA tetraloop receptor. I don't know really anything about biochemistry, right? But it's some biomolecule which had a little wing which would dock up against the parent strand. Right? So this thing would basically wiggle back and forth. And what we did was stuck 2 dyes on this molecule, one on the wiggly port and one on the dock. And depending on how close together these 2 ends were, you would get efficient or inefficient FRET, fluorescence resonance energy transfer. And basically what we could monitor was the color of light that was emitted from these 2 dye molecules as a function of time. That's shown here. So you can see this kind of digital binary behavior, right? Sometimes it has a FRET efficiency up here. This is associated with one color. Sometimes it has a FRET efficiency down here. This is associated with a different color, right? And depending on the area under these 2 curves, we could back out, you know, how much time it spent docked versus how much time it spent undocked. We would then do this at different temperatures. Right? So we get equilibrium constants at different temperatures. And we made plots of natural log K versus 1/T. Right? This is exactly what you do in Clausius-Clapeyron. Right? The slope of this plot is delta H over R, right? Which is exactly what we were reporting here. So these are real things that people do in the real world. I'm happy to talk to you more about any of this if you're interested in learning. Okay, I'm going to stop here. I have some problems up on the worksheets for you, and I will see you next time for a discussion of kinetics.